squared, typically up to about 1%. If you replace the mass of electron by the mass of the muon, but only keep these three amplitudes, which are conserving the lepton helicity, you will go to these curves. So these red curves here, which will enhance the effect. And if you take the lepton helicity flip amplitudes into account, there is a cancellation effect, and typically you will go to less than 0.5%. So what is predicted here is that these two photon corrections are smaller, typically less than 0.5% in the case of the muon. So this will be independent confirmation to see. And I think I will stop at this point because this will be another subject. And so this is open then for questions. And tomorrow, on Thursday, I will give my third lecture.
Questions?
So, using the dispersion relation you show as the sigma to gamma, but can the dispersion relation also to explain the PL and the PT? Because in the model calculation, for example, in the hadronic calculation, PL PT is equal to smaller than 1, and for the hadronic, the Photon calculation is but two different model, rather different result.
So, okay, this is the best here which is done right now. For right now, the dispersion calculation can only do this reliably at low Q squared. So, so at low Q squared, the band, this is an expanded scale here, of course, but the band is consistent with the data right now. So at larger Q squared, the input in the dispersion relation is not reliable enough to do it yet. So this work is still going on. It's all relatively recent. So one can do calculations, but if the input is not reliable, then
sure.
I mean here we show an error estimate. So you have a band. Yeah, the band would then be just too big. And
so the dispersion relation can talk about the PL itself or PT?
Yes, separate.
But still the same issue for the high Q squared, you don't have enough good input data.
Well, at high Q squared, the data input for the dispersion relation is not good enough. But the aim, of course, of this work is, the question is always why do you need it? Yeah? So why do you need high accuracy? At large Q squared, okay, typically people like to extract form factors with 10% precision,
yeah.
So that's enough. But if one wants to get radius extraction below 1%, then you have to work harder. So this formalism, the main motivation was, of course, to do it at low Q squared because this is where we need the higher precision. So that's why, yeah, I don't worry too much right now about larger Q squared. But in principle, if you improve the input, yeah, one can do that also.
More questions? I have one question. So in the muonic atom application, so for the two photon exchange contribution in that case, do you need to go through machinery to use 6 form factors?
No. Actually, it's a very good question, yeah. So I've shown you this in a different way last time. I've shown you this because in the case of the muonic atoms, so the momentum transfer is 0. So you have the same momentum coming in and out of the blob. So which means you can parameterize it in terms of 2 unpolarized structure functions, T1 and T2. Now, and we have used directly the data of the forward structure function, and then we have done the loop integral in Euclidean space, you remember? Yeah. Now it's, of course you can ask yourself, so why not doing it here with this formalism, directly parameterizing the 2 photon amplitudes? If you would know them, somehow you can also predict then the muonic atom. Now, because the muon is basically at rest in the atom, you will need, of course, the mass term. So you need 6 amplitudes. So it's just more complicated, but it means there is a constraint. So the 6 amplitudes are constrained already by the forward structure functions. So that's why this would be a big detour to do it from these 6 amplitudes. We did it directly using the forward structure function because they are well known. So but in principle, yes. So actually, analytically, we have expressed those relations. So these relations exist, but from a practical point of view, right now, because these 6 amplitudes are not known, they have not been applied.
Right. More questions? Okay, let's thank Marc for this interesting lecture.